You know, for decades, we've all looked at the Large Hadron Collider as our main window into the, frankly, bizarre world of quantum physics. But what if we've been using the wrong map this whole time? Today, we're going to look at the incredible things happening at the LHC through a completely different lens, the hard, predictable world of mechanical engineering.
Okay, so let's just start with one big question. I want you to forget about quantum foam and invisible fields for just a minute. What if smashing protons together isn't about conjuring up magical new particles, but is actually a stress test? Like a literal test of the ultimate breaking point of the universe itself.
On one side, right, you've got the language we all know from physics class, a universe run by probabilities, invisible fields that somehow grant mass, and these mysterious collapsing waves. But on the other side, well, that's the language of a machine shop. Stress, strain, drag, and the absolute breaking point of a material. Today, we're diving into the idea that the universe, even at its very smallest scale, is a physical machine. So here's the game plan. We're going to run a full-on materials test on reality itself. Seriously, we'll start by figuring out what material we're even testing. Then we'll apply pressure, watch for resistance, push it right to its limit, and then we'll analyze the failure. It's a wild ride from the fabric of space all the way to the creation of matter.
First things first, we have to completely shift our perspective. The core idea here is to stop seeing the LHC as a particle creator, and start seeing it as a heavy-duty materials testing machine. It's not creating particles out of some abstract energy, it's actively testing the shear strength and the structural limits of the vacuum.
So if we're testing a material, what is it? Well, it's the one thing we've always been told is nothing. Empty space, the vacuum. But in this mechanical model, the void is anything but empty. In fact, it's the strongest thing there is. It's called the Universal Lattice. Try to picture it like this, a continuous, perfectly symmetrical, and unbelievably rigid structure. It isn't made of particles, it's the underlying grid that allows particles to even exist in the first place. It's basically the structural engine block of the entire cosmos.
And this quote just nails it. We're not floating around in some empty nothingness. We are living inside the most robust physical material you can imagine, a structure that's been pre-stressed, loaded with tension ever since the Big Bang.
And get this isn't just some wild idea pulled from thin air. It connects directly to things we already know. I mean, quantum field theory tells us that a perfect vacuum is actually boiling with something called zero-point energy. Now, standard physics might see that as random quantum jitters. But an engineer? An engineer sees a loaded spring. That boiling energy is the proof of the tension locked inside the universal lattice.
Okay, let's get to the first part of our stress test, speeding up a proton. Now, we've all heard the line, right? As you get closer to the speed of light, your mass increases towards infinity. Well, this mechanical model says, nope, that's not what's happening at all.
Think about it. Do particles really just create infinite matter out of nowhere because they're going fast? That feels more like a mathematical quirk, not a physical reality. The real story isn't about the particle, it's about the medium it's trying to plow through.
You see, the speed of light isn't some magical cosmic speed limit. It's just the natural resonance speed of the universal lattice. It's the absolute fastest that the fabric of space can get out of the way, warp, and snap back. It has a bandwidth, just like any physical thing does.
So here's the key idea. What we call relativistic mass gain is actually something called total solitonic impedance. It's not more mass, it's more drag. A particle is just a little knot of energy. And when you try to force that knot through the super rigid lattice at nearly its top speed, the resistance, the impedance, becomes absolutely immense. The universe pushes back hard.
And look, this isn't just a concept, it's modeled with math. This equation here shows that as the particle's velocity, that's v, gets closer and closer to CR, the speed of light, the drag just shoots toward infinity. So the LHC isn't making protons heavier, it's fighting the incredible structural resistance of space itself.
And that brings us to the collision. This is it. Two protons, each pushing a massive shockwave of this impedance in front of them, about to smash head-on. This is the moment of maximum stress, where we're about to test the absolute compressive strength of the universal lattice.
In engineering, right, every single material has a yield point. It's that limit where it can't bend anymore, and it has to either permanently change or just break. Well, according to this model, the vacuum is no different. It has a limit. It has an ultimate compressive strength. You can only squeeze it so far. So let's just walk through this insane moment. The proton shock waves collide. Bam! All that kinetic energy forces the lattice at that tiny, tiny point into an extreme state of contraction. The pressure just skyrockets until it hits the vacuum's absolute structural limit. And right there, the system is maxed out. It has hit the microscopic yield point.
So what happens now? A physical system can't just hang out at its breaking point forever. So what happens in that infinitesimal moment when the very fabric of reality is squeezed beyond its absolute capacity?
It recoils. To survive, to avoid total structural failure, the system does the only thing it possibly can. It executes a mandatory, violent mechanical recoil. It snaps back. This event is called the Vidyabhushan bounce. It's essentially a rapid phase shift. The lattice can't be crushed into nothing, so all that stored up energy has to escape somehow. The whole system forcefully snaps into a new geometric shape just to dump the excess load and find balance again. It's a survival mechanism.
And this, for me, is the most amazing part. That shower of new particles that the LHC detects, it's not a magical creation event. It's the physical debris from the snap. It's structural shrapnel. The really heavy, unstable particles you see are just the leftover vibrations of the lattice trying to calm down. And the lighter, stable particles are the final state, once that little piece of space gets back to normal.
So, okay, we've gone from the impossibly small, but how does this connect to, well, everything? The idea here is that this microscopic snap we see in the LHC, it isn't some unique one-off event. It might actually be a tiny echo of how the entire universe got started.
I mean, look at the parallel here. It's perfect. In the LHC, protons collide, pushing a tiny spot of the lattice to its limit, causing a recoil that spits out new particles. In this model, the Big Bang was a cosmic snap, where the entire pre-universe was compressed to its absolute limit and then recoiled, creating everything we see. It's the same engine, just on a completely different scale.
This just reframes our whole understanding of reality, doesn't it? It suggests we don't live in a universe of random chance, but one of structural integrity, stress, and recoil. And it leaves us with one last, pretty profound thought. If the fabric of reality is a machine that snaps under pressure, what happens when the pressure starts building again?